In this episode, I'll discuss polar coordinates and their relation to Cartesian coordinates, which you're already accustomed to working with. I'll start by fixing a point O, called the pole or origin, and an initial ray called the polar axis. Each point in the plane can be represented or assigned polar coordinates r, theta, where r is the directed distance from O to P, r may be positive or negative, and theta is the directed angle from the polar axis to the segment OP. Theta is positive when measured counterclockwise and negative when measured clockwise. With Cartesian coordinates, each point in the plane has a unique representation. However, each point in the plane has infinitely many pairs of polar coordinates. For this example, let's find all the polar coordinates of the point P, 1, pi over 2. I'll start by plotting the point. So starting at the polar axis, measure counterclockwise pi over 2 radians. Then the point 1 unit from the origin along the ray, theta equals pi over 2, has coordinates 1, pi over 2. The angle associated with this point is not unique. For example, an angle of measure pi over 2 plus 2 pi radians would also work. So we need to find the angles for all coordinate pairs in which r equals 1. These angles are pi over 2 plus integer multiples of 2 pi. So here k is an integer. Notice we could also obtain the point P by starting at the polar axis and measuring clockwise pi over 2 radians and moving backward 1 unit. So negative 1, negative pi over 2 also describes the point. So we also need to find angles for all coordinates in which r equals negative 1. These angles are negative pi over 2 plus integer multiples of 2 pi. Again, k is an integer. So summarizing, this is the set of all polar coordinates for the point P. When you look at the first ordered pair and take k to be 0, we have 1, pi over 2. Second ordered pair, when k is 0, we have negative 1, negative pi over 2. In the next video, we'll discuss graphing in polar coordinates in more detail. So for now, I'll just discuss a few basic polar equations. The first equation is r equals a. Here we fix r at a constant value of a, and we let theta vary. So as theta varies over any interval of length 2 pi, the point P traces out a circle of radius absolute value of a centered at the origin. The next equation is theta equals theta naught. Here we fix theta at the constant value of theta naught, and we let r vary from negative infinity to infinity. So P traces a line through the origin with a measure of theta naught from the polar axis. To establish the relationship between polar and Cartesian coordinates, we let the polar axis coincide with the positive x-axis and the pole coincide with the origin, as you see in this figure. If r is positive, we can use this right triangle to establish the following relationships. The first is cosine theta equals adjacent over hypotenuse, or x over r, meaning x equals r cosine theta. Next, sine of theta equals opposite over hypotenuse, or y over r, which means y equals r sine of theta. Another relationship we have is that r squared equals x squared plus y squared. And finally, tangent of theta equals opposite over adjacent, or y over x. Now, it can also be shown that for r less than 0, these relationships hold. And so I'll summarize them here. These relationships allow us to convert coordinates or equations from one system to the other. And that's what we'll look at next. In this example, we'll convert from polar to Cartesian, which is very straightforward. We want to find the Cartesian coordinates for the point 2, pi over 3. Well, x equals r cosine of theta. In other words, x equals 2 cosine of pi over 3. So x is equal to 2 times 1/2, or 1. And y equals r sine of theta, or 2 sine of pi over 3. So 2 times root 3 over 2, or root 3. Therefore, the Cartesian coordinates for this point are x, y equals 1, root 3. Let's go in the other direction, convert from Cartesian to polar, find one set of polar coordinates for the point 1, 1. I'll start by determining theta, and we can use the equation tan theta equals y over x, or in this case 1 over 1, which implies theta equals tan inverse of 1. So we have theta equals pi over 4. Because this angle theta lies in the first quadrant, the same quadrant as our point 1, 1, we use positive r. R equals square root of x squared plus y squared. So square root of 1 squared plus 1 squared equals root 2. And therefore, one set of polar coordinates for this point is root 2, pi over 4. As we have seen, point conversion from polar to Cartesian is straightforward, while point conversion from Cartesian to polar is more involved. The opposite is true for equations. To convert a Cartesian equation to polar form, we simply replace x by r cosine theta and y by r sine theta. Converting a polar equation to Cartesian form can require more effort and ingenuity. Let's replace the Cartesian equation x squared plus y squared equals a squared with an equivalent polar equation. I'll begin by replacing x with r cosine theta and y with r sine theta. Next, I'll square each term to get r squared cosine squared theta. Sine squared theta equals a squared. Factor out an r squared on the left-hand side. And now replace cosine squared theta plus sine squared theta with 1 using the Pythagorean identity. So we have r squared equals a squared. Taking the square root of both sides, r equals a, or r equals negative a. And if you think back to the previous slide where we looked at the graph of the equation r equals a, this is a circle with center at the origin and radius a. In this final example, we'll replace the polar equation r equals 1 minus cosine theta with an equivalent Cartesian equation. And this is the direction that often requires a little more work and ingenuity. So here I'll begin by multiplying both sides of the equation by r to obtain r squared equals r minus r cosine theta. That allows me to replace r squared with x squared plus y squared, and r with plus or minus the square root of x squared plus y squared, and of course r cosine theta can be replaced with x. Adding x to both sides, we obtain this equation. Next, I'll square both sides of the equation, which gives me this, and bringing all terms to one side, we have this. And the graph of this equation is what's called a cardioid. So summarizing, what are the things to take from this video? Well, each point P in the plane can be assigned polar coordinates r, theta, where r is the directed distance from the origin to P, and theta is the directed angle from the initial ray to the segment OP. The relationships x equals r cosine theta, y equals r sine theta, r squared equals x squared plus y squared, and tangent theta equals y over x allow us to convert coordinates or equations from one system to the other.